Is this okay? Let me see.
Okay, it's my great pleasure to introduce Gang Liu from China, and he will tell us about Kähler manifolds with curvature bounded from below. Please go ahead.
Thank you very much for the introduction. It's my great honor to speak here. So today I will talk about my recent works on Kähler manifolds with curvature bounded below. So the talk is divided into two parts. The first one is the uniformization conjecture and related problems. And the second would be about the Gromov-Hausdorff convergence on Kähler manifolds. Okay, so let us start with the classical uniformization theorem. Let M be a simply connected Riemann surface. Then it is isomorphic to P1, C, or the Poincare disk P2. A geometric consequence is the following corollary. So let M be a Riemann surface if M admits a complete conformal metric of positive curvature, then it is isomorphic to P1 or C. The natural question is, are there generalization for half-dimensional Kähler manifolds? So let us just focus on the bisectional curvature case. So let M be a Kähler manifold. So we say the bisectional curvature is positive if R, I bar, J bar is positive for any two non-zero vectors, EI, EJ, in the holomorphic tangent space. In the late 1970s, Mori, Siu, and Yao solved the famous Frankel conjecture. So let M be a compact Kähler manifold with positive bisectional curvature, then M is biholomorphic to the complex projective space. A remark is that Mori actually proved the stronger Hartshorne conjecture. The non-compact analog was proposed by Yao in the 1970s. The so-called uniformization conjecture says that if M is completely non-compact Kähler with positive bisectional curvature, then it is biholomorphic to the complex Euclidean space. Now, let me introduce a definition which is related to some problems below. On a complete Kähler manifold M with a base point x0, we say a holomorphic function f is in ODM if the norm of f is bounded by a constant times a polynomial of the distance. So we also define the OPM as the union of all OPM. So it is clear that OPM is always a ring. Let us also state some related problems. The so-called finite dimensionality question says that if M is a complete non-compact Kähler manifold with non-negative bisectional curvature, then for any d greater than 0, the dimension of ODM is bounded by the dimension of ODCM. On the existence, here we mean the existence of polynomial growth holomorphic function. So assume M it has positive bisectional curvature. Okay. So we always assume the manifold is completely non-compact. Then the following three conditions are equivalent. The first one says that there exists a polynomial growth holomorphic function, and the second says that the manifold has maximal volume growth. In other words, the volume grows like is kind of proportional to the Euclidean the volume of the Euclidean ball up to a factor. because here the manifold has a real dimension 2n. Okay, so out of the 2n is basically that's the order of the volume of the Euclidean ball. The last one says that there exists some constant c independent of r, so that the average of the scalar curvature over a geodesic ball is bounded by c over r squared. Basically, it has quadratic decay. Okay, so this conjecture says that such three conditions are equivalent. Okay, so okay, and also the finite generation conjecture says that if we have a Kähler manifold complete non-compact with non-negative bisectional curvature, then the ring OPM is finitely generated. Okay, so we notice that OBCN. Okay, so you consider the CN with a flat metric. So OBCN is identified with the polynomial ring, and that's generated by the coordinate functions z1, z2, up to zn. Okay. Okay. So on this, we will come to these four conjectures. The finite dimensionality conjecture was solved by Ni, Chen, Fu, Ying, and Zhu. Okay. So they gave in addition, they also characterize the equality, as it says that if it holds for the equality holds for some integer d greater than 0, then the manifold is biholomorphic and isometric to C. So the key in the proof is Ni's monotonicity formula for heat flow on Kähler manifolds with non-negative bisectional curvature. Later, we discovered a three-circle type theorem which gave an alternative proof to the finite dimensionality conjecture. Okay, so the definition. So we assume M is a complete Kähler manifold. Then we say M satisfies the three-circle theorem if for any point P on M, any holomorphic function f on the geodesic ball BPR, and you have that log MR is convex of log R. In other words, the following inequality holds, where MR is the supremum of F over this ball. By a classical result of Hadama, we know that the three-circle theorem holds for Cn. Question is, can we classify all Kähler manifolds satisfying the three-circle theorem? And the result says that it satisfies the three-circle theorem if and only if the holomorphic sectional curvature is non-negative. So in other words, we only require such curvature be non-negative. So in particular, if M has non-negative bisectional curvature, then the three-circle theorem holds. The proof is a simple combination of the Hessian comparison and a maximum principal argument. Corollary is the following sharp monotonicity formula. So if M has non-negative holomorphic sectional curvature, and you assume that F is in ODM, that is to say, F has polynomial growth of degree at most D, then MR over R to the D is monotonic non-increasing. The corollary just follows by letting R3 approaching infinity in the three-circle theorem. Okay, so now let us give a simple argument of the following theorem. So if H is greater than or equal to 0, then for any D greater than 0, the dimension of ODM is bounded by the dimension of ODCN. So we argue by contradiction. Assume the inequality fails for some D greater than 0, then by linear algebra, at any point P on M, there exists a non-zero holomorphic function f in ODM such that the vanishing order at P is at least the integral part of D plus 1. Then we know that the limit of MR over R to D is 0. But the corollary says such a quantity is non-increasing. Then F is identically 0. So this is a contradiction. So we can also characterize the equality case. And the conclusion is the same as in the theorem, previous theorem, as Ni, Chen, Zhu, Yin, and Fu. Okay, so by establishing the three-circle theorem for the negative curvature case, we obtain the following. Okay, so in this case, we do not assume the strict non-negativity. So let us assume that there's non-negative curvature outside a compact set K, and you assume minus A as a lower bound of the holomorphic section curvature, and you define this lambda as A times the square of the diameter. Then there exists a constant C depending only on this lambda and the dimension, such that such inequality holds. And this notice that the power is sharp. Finally, also, if D is kind of small, then we actually have the sharp dimension estimate. So we remark that if D is large enough, then the sharp dimension estimate, I mean the last inequality, does not hold. So D has to be small. So say less than 1 over 2 lambda. Okay, so now let us move to the existence conjecture. So previously, Ni and Ni Tan proved that condition A is equivalent to C. So recall that it says that the existence of a non-constant polynomial growth holomorphic function is equivalent to saying that the average of scalar curvature has quadratic. Their proof used the heat flow method. The key is to solve the Poincare-Lalonde equation. Later, we managed to prove that A is equivalent to B. In other words, the existence of a non-constant polynomial growth holomorphic function is equivalent to that the manifold has maximum volume growth. So putting these two things together, we get that so we can solve the existence conjecture. Okay, so now let me explain a little bit how to construct non-constant polynomial growth holomorphic function. Let's say assume manifold has maximum volume growth. So usually this was done by finding PSH function of logarithm growth. Then you can solve the Hermann's error estimate of d bar. Here we take a different approach. The idea is to look at the tangent cone of M at infinity. So according to Kähler and coding, on the geodesic ball EPI1, there exists a rho I close to R squared over 2 pointwise, such that the following L2 Hessian estimate holds. Now, consider the heat flow of rho in a short time. Then, because of the curvature condition, we find that the rho T will immediately satisfy that the DDC of rho T is strictly positive. So this is crucial for solving the d bar problem. Then then we can find holomorphic function on BPI1 with some good estimates. Notice that this corresponds to a holomorphic function or on BPRI, where Ri is large. So now the point is to take the limit, right? Because we want to get a global function. So such function is only local, so it's only on BPI1. And so we obtain the holomorphic function on larger and larger domain. Then we are in a position to apply the three-circle theorem. So by a suitable normalization, we can take subsequence to get a non-trivial polynomial growth holomorphic function. So we emphasize that the tools we used were the Gromov-Hausdorff convergence theory, Hermann's L2 estimate of d-bar, heat flow techniques by Ni and Tam, and also the three-circle theorem. Now we move to the finite generation. So in early 1980s, Mach proved the following. So assume M is a complete non-compact Kähler manifold with positive bisectional curvature, maximal volume growth, and quadratic curvature decay. Then it is biholomorphic to a affine algebraic array. So Mach actually proved that in this case, OPM is identified with the affine coordinate ring. Thus, it is finitely generated. Later, under the assumption of non-negative bisectional curvature, Ni proved that the transcendental dimension of OPM over C is at most n. So a few years ago, we managed to solve the finite generation potential. So we also obtained a partial result for the uniformization potential. So basically, you assume non-negative bisectional curvature and also the maximal volume growth. Then we can obtain that the manifold is biholomorphic to a affine, right? The idea is based on the resolution of the existing conjecture. It was built on that, but slightly more than that. Okay, so assume M admits a non-trivial polynomial growth holomorphic function because you want to prove the finite generation. So without loss of generality, you can assume there is a non-constant polynomial growth holomorphic function. If we cheat a little bit, say the universal cover does not split, then we can prove that it has maximum volume growth. So now the key point is to prove that there exists finitely many polynomial growth holomorphic functions such that the map is proper. So again, this heavily uses the trigger coding TM and the three-circle. So on the uniformization, it is open so far. However, there has been much progress due to various authors. For example, Mach, Xiu, Yao, Shi, Chen, Zhu, Ni, Chao, Tam, Liu, Wang, He, Li, etc. Okay. So in the 1980s, Mach, Xiu, and Yao and Mach, they considered embedding by polynomial growth holomorphic functions. Later, Shi initiated the Kähler-Ricci flow approach. Results were improved significantly. So in 2004, Chao and Tam were able to prove that if M is a complete non-compact Kähler manifold with bounded non-negative bisecting curvature and maximum volume growth, then it is biomorphic Cn. The proof uses Kähler-Ricci flow and complex dynamics. In 2017, we proved that so basically we remove the boundedness of curvature. A remark is that Li Tan gave an alternative proof at the same time as ours. Their proof uses the Chern-Ricci flow. Okay, so a remark. Our proof uses the techniques from the finite generation. However, it is not straightforward to prove that a affine algebraic rate is Cn. So the key point is to study linear functions, linear space of holomorphic vector fields that preserve the degree of polynomial growth holomorphic functions. Okay, so a detailed analysis gives us the canonical holomorphic coordinates given by polynomial growth holomorphic functions. A remark is that recently, Chen and Zhu obtained some important results when the volume does not have maximum volume growth. Okay, by using the techniques above, we also obtain compactification of certain non-compact Kähler manifolds. So we assume that it has non-negative Ricci curvature and the maximum volume growth. Let us assume that the curvature has quadratic decay pointwise. If M is Ricci flat, then it is biomorphic to a Grabin resolution of the affine algebraic rate. If it has positive Ricci curvature, then it is quasi-projective. This theorem is related with many previous results. For example, Bandel, Nakajima, Tian, Yao, Heil, Collin, etc. The first part generalized a result of Tian. He assumed that the curvature has faster than quadratic decay. And the second part generalized a result of Mach. Okay, so now let us move to the second part. Recall the seminal work of Kähler. Given K, V, D, N greater than 0, you consider a class of compact Riemannian manifolds with bounded section curvature, diameter, and also lower bound of volume. Then such class is pre-compact in the C1 alpha topology. In other words, you can always take a subsequence. So in the Kähler-Gromov sense. Later, Anderson generalized Kähler's theorem to the Ricci curvature set. So he assumed that the boundedness of Ricci and the lower bound of the injectivity radius, also the upper bound of the diameter. In this case, Kähler's theorem also holds. A remark is that Anderson's theorem satisfies the volume non-collapsing condition automatically. Okay. And the second thing is that one cannot replace the injectivity radius bound by the non-collapsing condition. Otherwise, the limit may not be smooth. So, in order to obtain pre-compactness, when the limit is not smooth, one has to consider weaker convergence. An important notion is the Gromov-Hausdorff distance. So, the fundamental result of Gromov says that if you consider a class of compact n manifolds with Ricci bounded from below, diameter bounded from above, then this class is pre-compact in the Gromov-Hausdorff sense. We know that the limit may be far from smooth. So in fact, this theorem also holds for non-compact case if one considers the notion of pointed Gromov-Hausdorff continuous. A basic problem in metric differential geometry is to study the regularity of the Gromov-Hausdorff limit of manifolds with Ricci curvature bounded from below. One can also assume the volume is non-collapsed, say for simplicity. But this is not necessarily required, I should say. There are fundamental contributions by Kähler, Cody, Tian, Neighbor, etc. Let us consider a point given limit space X and point X, P. We can consider blow-up. A blow-up limit is called a tangent cone. Notice that this is not necessary. A point on the limit space is called regular if a tangent cone is isometric to the Euclidean space. And so the complement is called the singular set. Below is a fundamental result of Kähler and Cody. So let X be a pointed Gromov-Hausdorff limit of sequence of manifolds with Ricci bounded below. So we consider normalization. And the volume is non-collapsed. Then X is a metric length space of Hausdorff dimension n. Also, the Hausdorff measure is equal to the limit of the volume element. The singular set has Hausdorff dimension at least 2, which is sharp. And any tangent cone is a metric cone. So for simplicity, let us call X a non-collapsed Ricci limit space. This theorem tells us that most points on X are regular. However, we notice the following. Regular points are not so regular. For example, consider a double disk. Then all points are regular. And near the boundary of the disk, the metric is only Lipschitz. It is conjectured that near a regular point, the metric is by Lipschitz to a Euclidean ball. Currently, the best known regularity is by Holden. The second thing is that regular set is not necessarily Holden. In other words, the singular set is not closed necessarily. In fact, it could be dense. Okay. So in higher dimensions, Li and Nam consider a limit space so that the singular set is a fat counter set. So in the above, we consider the limit of Riemann manifolds with Ricci curvature lower bound and non-collapsed volume. What if these manifolds are Kähler? So the first important result is by Kähler, Cody, and Tian. So they prove that for any Kähler-Ricci limit space, tangent cone splits even dimensional Euclidean factor. In other words, the splitting lines must come in pairs. Below is a very remarkable result, breakthrough result. We only list the part for the purpose of the talk. So assume X is a Gromov-Hausdorff limit of a sequence of polarized Kähler manifolds with bounded Ricci diameter and volume. then it is homomorphic to a normal projective gradient. So in the joint work with Takehide, we generalize the result to the case when the Ricci curvature has a lower bound. The argument follows from the breakthrough result, and the key step is Tian's partial C0. So we also need a deep result of Kähler, Jiang, and Neighbor on the Minkowski content. So a basic technical ingredient is a result on the fixed size holomorphic chart in balls that are Gromov-Hausdorff close to the Euclidean ball. So there exists epsilon greater than 0 depending only on dimension is the following problem. Assume this ball with radius epsilon to the -1 is close to the ball on Cn, okay, with the same radius. Then we can find a fixed size holomorphic chart. Okay, so and also on the unit ball, we can write the Kähler potential omega as dT bar of rho, where rho is pretty close to the square of the distance. Here, limit of psi is 0 if epsilon goes to 0. Okay, so remark is that if the manifold is merely Riemannian by its Kähler coding, then prove that there exists a harmonic chart of fixed size. So we are given a stronger assumption that the manifold is Kähler. Then we find a fixed size holomorphic chart. Okay, so let us mention the strategy to the holomorphic regularity. So basically, we need to run the Ricci flow. So actually, it's a the new metric is not necessarily Kähler. Okay, so and but now the point is that we obtain the metric which is almost compatible with the complex structure. Okay, the new metric, and by the Nuremberg theorem, by the approach, we can find a fixed size holomorphic chart. And we glue such chart to a domain of CPN. And then we run the genuine Kähler flow. Finally, the desired holomorphic chart followed by solving the another D-bar problem. Okay, so we skip details. So two applications. The first one is that under the Gromov-Hausdorff convergence to a smooth manifold, Riemannian manifold, the scalar curvature function converges as measures. Okay. So the corollary is that if a Kähler manifold, a geodesic ball, is sufficiently close to the Euclidean ball, and say the Ricci has a lower bound, then the integral of the scalar curvature is small. Notice that there is no way to control the scalar curvature pointwise, because the closeness is only in the Gromov-Hausdorff sense. The key point is that with such assumption, we were able to find fixed size holomorphic chart. And there you can write the Ricci in this form. Then you can apply the Kähler coding and also the Gromov potential theory. A second corollary is the following. It says that if you have a complete non-compact Kähler manifold with non-negative Ricci curvature, and then the volume or symptotic volume ratio is very close to the Euclidean volume, then it is biholomorphic C. Remark is that if the manifold is merely Riemannian, Perelman proved that the manifold is intractable. Shiger-Cody proved that such manifold is diffuse to the Euclidean space. So basically, we assume a stronger Kähler assumption, and we obtain a stronger result. Let us also study the structure of the singular set. Recall the result of Donaldson and Sun. They assume a sequence of polarized Kähler-Stein manifolds. Then the metric singular set is the same as the complex analytic set. Tangent cone is homeomorphic to normal variety, and also the tangent cone is unique. Okay, so we also obtained the analogous result when the Ricci has a lower bound. Okay, so basically it says that in this case, the singular set, so that is x minus r, so it's not necessarily equal to the set of complex analytic singularity. Instead, it is equal to a countable union of analytic sets. So it's slightly different. So recall previously we mentioned that the singular set could be dense. So even in real dimension, even in complex dimension 1. So the countable union cannot be replaced by a finite union. We also recall that Lee and Neighbor constructed a limit space in the real case, such that the singular set is given by a fat counter set. So in other words, the topology is rather complicated. So this tells us that the Kähler case is actually very different from the real case. Okay, so let me just explain the reason behind the countable union. Okay, so the key is the following characterization. So a point is regular in the metric sense if and only if it is complex analytically regular. Well, because on the limit space, we know that it is algebraic, right? So there is a complex analytic structure. But this is insufficient. And the second condition is that the long number for Ricci vanishes. Here, Ricci is a positive one current on the limit space. So this is regarded as a limit of Ricci form of manifolds. So with this in hand, the argument goes as follows. If a point is metric singular, then we know that it is either complex analytically singular or the long number of Ricci is positive. In the first case, it belongs to a complex analytic set. And in the second case, according to the theorem of Steele, the set is a countable union of analytic sets. So when the bisecond curvature has a lower bound, we can obtain the analogous result. Actually, it's a parallel. So notice in this setting, we do not need the polarization assumption. So later, Bamler-Wilkie, Lee Tan proved that in this case, x, the limit, is actually smooth in the complex analytic sense. Also, Lott developed a theory on comparison geometry of Kähler manifolds with bisecond curvature lower bound. Finally, let us also mention an algebraicity result. So let X be a non-collapsed Kähler-Ricci limit space. Okay. So here we do not assume the sequence of Kähler manifolds are polarized, just the arbitrary sequence. Assume Ricci lower bound and non-collapsed volume. And then you get the limit, then any tangent cone is homeomorphic to a finite algebraic range. Basically, in some sense, it says that the tangent cone emits a natural, we can build a natural algebraic structure on the limit space. So by applying results of Martelli, Sparks, and Yao, also Donaldson and Sun, we obtain the following color. So if M is a Ricci flat Kähler manifold of maximum volume growth, then the asymptotic volume ratio is an algebraic number. Basically, it says that it is always a so it's algebraic. So it's a solution to a polynomial equation with the integer coefficients. Okay, thank you for your attention.
So thank Gang Liu for this very beautiful and rich talk going all across from D-bar estimates to Ricci flow to Gromov-Hausdorff limits. So I think it was very, very nice talk. So thank you very much. So maybe I was muted, so I'll try again. So I would like to thank Gang Liu for this very beautiful talk, going all across of Kähler geometry, from D-bar estimates to
Okay, so